ASCII text character. And as you've already seen, you have the assignment operator, which is the single equal sign, and it's unfortunate that it's the single equal sign. That's a historic. There are historical reasons why it's the single equal sign, and it definitely is a misuse of the traditional equal sign, because if you were an equal sign in algebra, that would be saying that the thing on the left-hand side is equal to the thing on the right-hand side. But that's certainly not the case, because the thing on the left-hand side is a variable declaration, and the thing on the right-hand side is a value. Right? So the way that you read this is not an equals. We'll talk about equals when we look at conditionals on Monday. You use two equal signs there instead. But the way that you should read this is take the thing on the right-hand side and evaluate it. If it's a value, if it's an operation like A times B or something like that, evaluate its value and place it into the variable on the left-hand side. So the thing on the left-hand side can only ever be one variable, and you're assigning it a value to the thing on the right-hand side. You can do it at declaration like I've got set up here. I'm declaring an integer x, and I'm setting it equal to 10 immediately. Of course, you don't have to do that. You could have an int, say, int y. What value does it have right now? If it were a pointer, it'd be null. We'll get to pointers much later. Or if it's a reference, it would be null. It could be 0, right? That's a sensible default value. C does not say what it should be. So it completely depends on the operating system that you're on, the compiler that you're using, and a whole bunch of other factors. It could set it to 42 as a default, and it would still be compliant with the C standard. There are no default values defined in the C standard, so be careful. If you declare a variable like this, yeah, 99 times out of 100 it might be 0, but it's not necessarily. Right? It could be garbage. It could be what we refer to as dead beef. Right? So what is dead beef? Well, it's a way of writing hexadecimal. Dead beef. Right? It's a word that you can spell out using the hexadecimal letters A through F. Often it's been used as a flag value to indicate that it has not yet been set. Or some other flag values have been used in the past. And compiler writers are allowed to do that. They could rewrite, you could rewrite GCC and set it equal to -42 for whatever reason, right? It would be kind of weird to do that, but it's still compliant with the standards. So there could be garbage in here. We don't know what is stored in Y. And if you don't know what's stored in Y, if it's just garbage, garbage times 10 is what? Garbage still. So it's best to always initialize your values to something that you think is sensible. For example, you could set it equal to 0 initially. You're always allowed later on to change a variable's value. That's why we call them variables, because they can vary. I'm simply going to change its value to 20. In this program, from this point down to this point, its value is 10. And at this point and beyond, its value is changed to 20, unless we change it again. You can declare and set a double variable, right? You can go ahead and set it to 3.14, or you can set it to 3. Implicitly, that means 3.0. I'll change it back to the original, though. When you declare a character value, however, you use single quotes, and you can only put in one single character. In this case, my first initial is C. Right? You could go ahead and change this to, say, /n. Right? That is technically one character, because that backslash there is an escape sequence. What is /n? What does that correspond to again? The end line character. If you want to go down to the next line, you can't simply just type enter, right? Because you're actually literally typing into your source code. So in order to tell the computer to go to the next line, you need to use /n. Likewise, we've got /t for tabs. We've got a couple of other things, but one thing that I want to know is, can I do a backslash? So can I do just one backslash? Probably not, right? In fact, you can see it right here. Maybe it's difficult to see in the back, but we've got a syntax error here. It's code highlighting. It's color highlighting. It's color syntax highlighting. This is going the opening single quote here is highlighted in green, but the closing one is in blue, right? So how do I get a backslash? What do you think? 2 backslashes, and that'll fix the problem. What if I want a single quote? Can I do this? Nope. What do I need to do? I'll need to also escape that. Right? So sometimes when you use the backslash, it is a backslash and then a following character that's treated as one character. Right? You can only ever put in one character here. If you tried to put in multiple characters, let's go ahead and see what happens. We'll go ahead and put it there. And first of all, it's complaining already. Let's go ahead and print this out. Print. What is the placeholder to print a character? Do you remember? We'll review it today. First initial. Right? And let's go ahead and run it and see if it actually runs. Nope. There's a compiler error here. Or actually, there's a warning, I guess I should say. 3 warnings generated. And I actually did end up printing S for some weird reason. It's printing garbage, basically. There's a warning that I said that this was a single character. I'm trying to force it to have 5 character values, actually 6, and we'll understand that when we cover strings in more detail. But you're not allowed to do that. My first initial is only a single letter. Okay? That's the assignment operator declaration of the 3 basic types. Okay? An identifier, a variable's name. And by the way, I've switched over to just typing in Markdown here. When I commit this to the repo and post it on Piazza, it'll be nicely formatted. It'll look something like, let's see, Markdown. It'll look something like this on the right-hand side, where all the code is nicely marked up. You've got math and stuff like that. It'll look much nicer. But again, I'm dealing with a bug in Atom.io right now. Right? So a variable's name, also called its identifier, right, because it identifies the variable, must follow several rules. Well, it may consist of capital letters, A to Z, and big A to big Z. It can include 0 through 9. It can include underscores and a few other things. But it may not begin with a number. Right? That's because it's just easier to not allow you to have variables named after numbers, because even if it's 0 foo, it starts to interpret 0 as a number, and then it gets confused. So we don't want to confuse the compiler. It's a dumb computer. Let's make sure that we help it along. It cannot begin with a number. Now, those are the basic rules, but it's much better to follow naming conventions. So style, use proper names. And what I mean by that is variables should be named after the things they represent. Right? Don't use non-descriptive variable names. For example, X would be a bad variable name. Now, in the context of a Cartesian plane where you're just talking about points, X and Y, sure, that's probably an okay variable name. But if you're talking about a first initial or the number of students, right, you would call those things what the variable represents, not just some mysterious variable X. Other bad examples, of course, would include those placeholders of foo or bar or baz that computer scientists and coders like to use all over the place as placeholder variables. Or even, say, I don't know, my variable, right? Or my variable 02, because I need another one now, right? That's completely non-descriptive. It makes your code completely unreadable. If you write code like that and leave it for any amount of time and come back to it, it's a complete mystery. What was variable 02 representing again? I have no idea. What was variable 01 representing again? I have no idea. You want to make your code readable, right? So name your variables after the things that they represent. Good examples would include, say, number of students, right? Or another example, I don't know, what do I have here? Annual percentage rate, right? Now, you could say, in general, you should avoid abbreviations, acronyms, and short versions, right? For example, annual percentage rate, this is only a generality. Annual percentage rate, that's very, very descriptive. You know exactly what that means, but it is kind of a long one to type out. So if in the context you understand what that variable is, what that acronym is, and you want to shorten that up to APR because you are doing a financial application, that's perfectly fine. If you have a bunch of students and you want to represent their NUID, everybody here at UNL would know that that's the Nebraska University Identification Number, right? But if you were writing it for another university, you would want to use that because, of course, it would not represent anything at that other university. Likewise, if you used KMS, is that kilometers per second or just kilometers, right? You want to be more descriptive. Be as descriptive as you want. And again, it's all a balancing act, right? You want to be Goldilocks about it. Not too short, not too long, just right, right? So it is a little bit of art when it comes to variable naming. In fact, there's an old saying that there are only two hard things in computer science: cache invalidation and naming things. So right there, that's one of the hardest things in computer science is naming things, right? But don't worry about it. All right. In general, follow consistent styling. So you'll note that my good variable names here followed what's called a lower camel casing convention. That is the first word, if it's multiple words, the first word is all lowercase. The beginning of each subsequent word, you make the first letter uppercase, but then everything else is lowercase. Obviously, you cannot have white space in your variable names, because if I have a variable foo, space, bar, those are two different things. Right? Spaces are kind of delimiters for a compiler for a programming language. You can use lower camel casing, or another common convention, especially with old school C, is lower underscore casing. Right? Now, I tend to not like that. Well, you can see the pattern there that everything is lowercase now. But to separate words, we put in an underscore instead so that it's kind of readable. You can't have a space, but the next best thing is going to be an underscore. The problem with that is if you're typing a lot of underscores, what are you doing to your hands? Where's the underscore? Way over here on this side of the keyboard. And to get to it, you need to type. It's the hyphen, right? To type it, though, what do you need to do? Take your pinky finger and move it all the way over to the shift and then hit the hyphen, right? And if you're doing that every other word, right? Every word, then your pinky finger is eventually going to fall off. So protect your pinky finger. Don't give yourself arthritis, and use a more modern styling convention of lower camel casing. We use lower camel casing because if everything were lowercase, it would be extremely difficult to read. But this gives you a nice visual cue of each word being separated. If it were just one word, say, I don't know, the example's up here, for example, pie, then everything is lowercase, and there's no multiple words, and so this is still lower camel casing up here. Okay? So follow consistent naming conventions. Otherwise, you can name it whatever you want, as long as it applies to these rules, and as long as you are using good descriptive names and using a consistent naming style. Okay? So those are basic variables. Once you've got basic variables, you need to do something with them other than just assigning and reassigning values. You'll want operators. Right? And what we mean by operators is you're going to be doing basic math. Right? There are arithmetic, and you start out with basic arithmetic. Right? There are arithmetic operators. For example, everybody knows what that is. What is it? Plus or addition. Right? Subtraction is, of course, going to be the regular old hyphen. And that's easy because those are on your keyboard, right? But what's not on your keyboard is a multiplication or a division symbol. So what's the next best thing? Asterisk or star and slash. What kind of slash is that? Forward slash. This is, again, addition, subtraction, multiplication, and division. Right? Not only that, but you've got, consider the following. Consider the following. What if I go with these two operations? A plus B times C versus A, in parentheses here, A plus B. Well, actually, no, forget it. Consider the following. Just consider this one. A plus B times C. How would you end up reading that? If it were written on a piece of paper, which operation would you end up doing first? B times C. Why? It's to the right. Right? You read left to right, right? No, instead what? PEMDAS. Remember PEMDAS. What is PEMDAS? PEMDAS. Parentheses, if I spell it right. Then what? Exponents. But we don't do exponents in C. As an aside here, some programming languages do allow you to raise x to the power y using this, the 2 stars. C is not one of those languages. I will show you how to do it later. Yeah. No, some languages also allow you to do it like this, x to the y. C does not allow you to do that. That's actually a bitwise exclusive OR. You can get that, but it's something completely different that deals with logic rather than raising something to a power. So parentheses, exponent, again, it's not part of C. I'll show you how to do it instead using the math library. Then what's the M? Multiplication, then division. So multiplication and division have an equal order of precedence, and you read it left to right. So if I've got A times B times C divided by D, then I would go those two multiplications first, and then the division. Right? So you would read it left to right. And then finally, addition and then subtraction. So I want to focus on that first one, the P, parentheses. If you did mean I want to do A plus B first, then this is not the same as if you put it into parentheses, A plus B times C. And let me go to the next line here. So it's not broken up. That is a completely different expression. Now, by putting parentheses around it, we've raised the order of operation, and that's going to be evaluated first. A plus B will be evaluated. That answer then will be multiplied with C. It doesn't cost you anything to write parentheses. Even if you don't need it, you still write it. Like if you want A times B plus C times D, go ahead and put parentheses wherever you want. Right? Don't put too many parentheses. Again, Goldilocks it. Yeah?
Isn't there a modulo operator?
Yeah, we'll talk about that next. Right? All right. So PEMDAS, just like in programming. Now, programming languages support PEMDAS. Why? Because that's how we as humans think. Mathematics is thousands of years old, and that's how we've been doing mathematics up until this point. And then programming languages simply adopted what we were doing. It's actually more difficult for a programming language, for a compiler, and for a computer to do things the way that we do versus the way that they actually do it. You know, it's called pre-order, post-order, something like that. Don't worry about it. It's beyond the scope. Basically, a good compiler is going to have to parse out what you want it to do, and then it's going to have to change the expression to do it how it's actually going to do it on the machine. Here's another example. Right? What if I wanted to do, say, let's see, negative b plus minus square root of b squared minus 4ac divided by, and don't worry about this, I'll show you how it's, let's see, frac. There we go. This is why I don't like showing you the raw markdown here, because I want to show you what it actually looks like here in a second. What should go on in the denominator? 2a, good. What am I writing there? The quadratic formula, right? And let's see if I wrote it correctly or if I screwed it up somehow. There we go. Jump all the way down to the bottom, and oops, zoom in, and it looks like I got it right. All right, except for the square root is a little bit off, but I'll fix that later. B squared minus 4ac. There we go. I didn't have square brackets instead, and there. square brackets on that, square brackets on that. There we go. So it'll render properly. Everybody knows the quadratic formula. Help me write that out in a piece of code here. Let's go ahead and create some variables first. Int a is equal to 10. Int b is equal to, I don't know, 1. Int c is equal to 20. Right, and I'll go ahead and increase the size here so you can see this. Let me go ahead and just get one root. So int root is equal to, how would I start writing that out? Negative b, right? So in other words, you can put negations here. Let me go ahead and expand this out. So you can put, and the negations actually have a higher order of precedence. That if you put a negative in front of a variable or a number, negative 10, then that will supersede everything else. Now I can't do plus minus, so we'll just do one of the roots, say the plus root. Now how do I go about writing square root? I could do something like raise it to 0.5, but we've already said that you can't use the caret. You can't use the multiplies. So what I'm going to have to do is I'm going to have to bring in a library here to do this. I'm going to have to bring in what you think that the library is called? The math library. There we go. Square root of, what was it? B squared. So how do I do b squared? Well, what is b squared? Simply b times b, right? So if it's simple enough, like square, just go ahead and use a regular multiplication. Or if it's cubed, just go ahead and b times b times b. Minus 4ac. Is that how you do it? No, you need explicit multiplication here. All right, so that works so far. Divided by 2a. Okay, well, 2 times a. All right. And some people like to put in a lot of white space here between all their operators. I'm not going to get fussy about it. If you want to, it makes it a little bit more readable. But that looks good. Let's go ahead and print it out, right? Printf. The placeholder for printing an integer is d, and the line. And we'll go ahead and print out the root, okay? One of the roots. Is this going to work? I've already violated PEMDAS. Why? What's going to happen? That denominator is tied to what? Where I go divided by 2a. It's only tied to the square root portion. The numerator is the entire thing up here. What do I need to do? Put parentheses around all of it, right? There we go. Is that good enough? No, why not? Now this is going to be divided by 2, and then the entire thing is going to be multiplied by a. So a is going to end up being in the numerator instead. So lots of parentheses, as many parentheses as it takes. Now, of course, you can go too far. You don't need parentheses here. That's kind of silly. So again, Goldilocks it just right. Let me go ahead and print this and see if it works. I'll go ahead and give myself some more space here. Does anybody know what the roots of a quadratic polynomial with coefficients 10, 1, and 20 should be? Ugh. Not that. Why? Actually, I'm quite surprised I got that. Weird. Like, %d result printf. Oh, okay. What's going on here? I'm kind of weirded out that I'm getting this value right here. There's not something I see immediately. But square root of why do you say it would end up being a negative number? I chose b to be very small, 1, and a is going to be 10, and c is going to be 20. So b squared, which is still 1, minus 4ac, some large number, what's that? That's going to be negative, right? Let me go ahead and strip this out and just have a square root of, say, negative 10. Or, yeah, let's just do it like this, and then get rid of that for now. What is that going to, what result is that going to be? Really, I'm really weirded out by this. Let me take this to the command line. Example.c. There we go. There's something obvious that I'm not seeing right now. %d root. It is an integer. Okay, fine. And let's go ahead and run it over here. I'm just getting the same garbage. Right. Well, I should be getting something else. I should be getting, oops. And it's not apparent to me what I'm doing right now. What I'm doing wrong, at least. I could jump. We're gonna save debuggers for later on here. Int root. Let's go with R instead. I don't know if it's having trouble with root or not. Okay, weird. Anyway, what's the square root of a negative number? It's going to be what I heard it before. An imaginary number. There's going to be an I in front of it. Like the square root of -4 is going to be 2i because it doesn't exist, right? It's a complex number. It's an imaginary number. The way that that's going to usually be realized here in C is going to be maybe it's because include stdlib. Oops, I can't imagine that was it, but we'll find out. Nope, that's not it. Anyway, some results result in errors. So let's go ahead and go into code mode here. For example, if I do the square root of -10, results in NaN. Let me go ahead and capture that into a variable. Double x is equal to. There we go. What does NaN stand for? What do you think? Not a number, right? Now it is a number. It's just a complex number. But complex numbers are not supported natively by C. You'd have to bring in a library to support them, or you'd have to write your own code to support them, and you would have a real part and an imaginary part, and then you'd have to do all of the convolutions and kind of stuff that goes along with complex numbers. Don't worry about it, right? Another bad thing that can happen is int x is equal, let's go with something else, y is equal to 10 divided by 0. What is division by 0? Good question. It is undefined. I mean, in mathematics, it's undefined. Now, as you approach, so if I go 10 divided by a, and a is initially 1, well, now it's 10. Now, if a is 1/2, then it's even larger. If it's 0.1, then it gets even larger. If the denominator, so here's my split, and here's the denominator. If it gets smaller and smaller and smaller, then that means that this ratio is getting larger and larger and larger. So as I approach 0, what is it going to become? It's going to become infinite, right? And so this may result in inf, right? Inf is short for infinite, okay? So be careful with those kinds of things, and you might have to deal with them eventually, all right? Or you might just upfront check. Am I about to divide by 0? If not, if I am, then don't do that and do something else. We'll talk about that when we get to error handling and conditionals, okay? You also have, as somebody already asked, you also have an integer division operator, and that is %. Right? Now, that's not percent as in 50%, 100%. It's an actual operation. It results in the remainder of a division. Okay? So let me go ahead and just give you some examples. If I go with, say, my first example here is 10 divided by 3. And again, this should be read as mod or modulo, right? Latin or something like that. So this should be read as 10 mod 3. Now, if you were to go back to grade school and do your long division, 3 goes into 10 how many times? 3, but there's a leftover, a remainder. What is the remainder here? 1, right? So this results in 1, a remainder of 1. Right? Another example, what if I go with 11 mod 3? What does that result? It results in 2. because 3 goes into 11 3 times, giving you 9, but then there's 2 left over, and so 2 is the answer. Right? What if I do, say, let's go with 10 mod 2? What is that going to result in? Results in 0. What if I did 11 mod 2? That's going to be 1. What if I did 12 mod 2? 0, 0, 1, 0, 1, 0, 1. What does that give you a tool to do? To determine whether or not the value stored in a variable is even or odd. What's its remainder? If its remainder is 0, then you know that it's even. If its remainder is 1, then you know that it's odd. Right? Likewise, if your modulus is 3, then you can tell whether or not it's divisible by 3. It has a remainder of 1 divisible by 3, or it has a remainder of 2 divisible by 3. Can you have a remainder of 3 divisible by 3? What happens? You just go back to the beginning. 3 goes into 3 once, and so you're back at 0. Okay. All right. So that's the division, the integer division operation. There's another pitfall called truncation. So consider the following piece of code. I'm going to go ahead and create a couple of variables here. Int a is equal to 1. Int b is equal to 3. Or let's go with 10 and 20. That's what I traditionally go with. And then double c is going to be equal to a divided by b. Okay? What's the result here? And at this point, I'm going to go back to REPL and see if I can get at least this one to work. We'll go ahead and print this out here. %f c. All right. So predict really quick what the result is going to be. What's 10 divided by 20? Well, I mean, mathematically, let's say. 1/2, right? So you should expect this to have a value of 0.5. Let's see if it works. It has a value of 0. Why? Because an integer divided by an integer has to be an integer. Right? This is just a quirk of statically typed language, of many statically typed languages. If I have an integer plus an integer, the result is going to be an integer. That makes sense. Integer minus an integer has to be an integer. An integer times an integer also has to be an integer. 3 times 2 results in 6. That's still going to be an integer. With programming languages, the division operation also results in an integer if both of them are integers. Integer divided by an integer has to be an integer. So 10 divided by 20 results in 0.5. What's the integer part of that? 0. So take the 5, chop it off, throw it away. What are you left with? Exactly what we got up there, 0. That's what's known as truncation. Right? So the result here is going to be 0. Right? When you have an integer, two integers in your arithmetic operation, the result is always an integer. Now, again, for multiplication, division, or multiplication, addition, and subtraction, this makes sense, and we don't care. That's exactly what we would expect. But if you have an integer divided by an integer, the result is an integer. So the fractional part is thrown away or truncated. There we go. That's what we mean by truncation. It's thrown away. It doesn't matter that C is a double able to hold 0.5. The operation itself is going to result in an integer, 0, and so that's why we get 0.0000 over here. Okay? So the way that you can solve this by temporarily making one or both of the variables into a compatible double type by what's called typecasting or explicit typecasting. So what I'm going to do is I'm going to cut and paste this code, and I'm going to make it work now. So I'm going to say, for the purposes of this operation, make a into a double variable. Now it's a double divided by an integer, which is going to result in a double. Right? You can do it with both if you really want to, but it's redundant and unnecessary. At least one of them needs to be. typecasted. And that's what we call this thing right here. I'm putting in parentheses, by the way, make this thing a double temporarily. It does not change the variable. Remember, a variable's type is fixed throughout its scope, its entire lifetime. A is still an integer. All we've done here is said, take that 10 and temporarily make it 10.0 and then divide it by 20. And the result will be 0.5. When I do this, everything should be hunky-dory. And I've got 0.5. Okay? I'll go ahead and put that in the notes here, 0.5. That's what's called explicit typecasting. And again, it only has to be done with 1. And this is actually what I was hoping for with my original example with the square root. You'll note that the original example I was doing with the square root, everything was an integer. So integer times an integer, that's fine. But when we get to square root, and the square root is also going to be fine. But then when you divide an integer divided by an integer, things are going to get wacky. And that's why we were probably getting that really weird result there. Okay? All right. That's truncation. Other pitfalls, again, would include invalid operations that we've already looked at with a square root of a negative number, division by 0, et cetera, et cetera. Another thing that you need to be aware of is the math library. We've already seen that you can use, it has a bunch of nice mathematical functions. For example, sine, you could have cosine, cos, you have tangent, etc. You also have, say, square root. And, weird, why didn't they spell square root? Well, the same reason they didn't spell out sine and cosine and tangent, right? It's because 40, 50 years ago, they needed to save space. When you counted computers when you counted computer memory in kilobytes, if you can save a few bytes here and there by shortening things up, you did it. Now, the vast majority of programming languages still have a library function called square root that still uses sqrt. And they still use cos instead of cosine. Why? Well, because that's the way that they did it 40 years ago, so why change it, right? And it's much shorter to type. Yeah?
Will the math library have or translate pi into the number pi?
I'll talk about that in a second here. I'll put it here. It also has a bunch of nice constants. I shouldn't say a bunch. The only two that I can think of off the top of my head are m sub pi and m sub e, right? Pi and e. Why do we put in m underscore and m underscore e? Why did they do that? What do you think? What? It stands for math, definitely. If you wanted to use a different definition of pi for whatever reason, and you wanted to define your own pi, go ahead. The m pi is still there for you to use, right? So they didn't want to do what's called polluting the namespace. Every time you define a variable, or in this case, these are preprocessor directives, every time you define a function, sqrt, once I've defined an sqrt function in the math library, that prevents you from naming any of your functions sqrt. What I've done is I've polluted the namespace. I've grabbed one of these identifiers that you can't use anymore. So one common workaround is to prepend everything with a special symbol. In this case, M standing for the math library. Think about if I'm bringing in a bunch of libraries. If I'm bringing in a library to do graphical user interfaces, and I'm bringing in a library to do some serious number crunching, and these two libraries have a function in there, say foo over here and foo over here, I really want to use both of these functions. Then I've got a big problem because the namespace has been polluted, and I need to find a workaround for that. And sometimes it's not all that easy. So what library writers will generally do is they won't just name their function foo. They'll name it whatever. Say that the library is called bar. They'll name it bar foo instead, so that it has this weird prepended name. Fine, but that means it probably won't collide with anybody else's definition of their functions. So that's why we've got that m sub pi right there. So it also has a bunch of nice constants, including pi. It's as accurate as possible. It's the best possible representation that you'll get out of a double. Okay? Has a bunch of nice mathematical functions. You can use it by using include math.h. Don't worry about the .h again. It stands for header file. We'll talk about that later. On CSE, you may need to manually link it in. And so what I mean by that is when you go to GCC your file, then you might need to use like what I was doing on the command line trying to get it to work. -lm, that's an L, that's not a 1. My program.c, right? -L stands for link in. Do you remember the process that I showed you last week, 1 week ago, where you start with your source code. That source code then gets assembled into assembly. That assembly code then gets compiled to machine code. Then all of those other libraries out there, the standard input-output library, the standard math library, they get linked in with your program to finally produce an executable. L is the linking process. What I'm doing here is I'm telling the compiler, yes, link in the math library. The reason that you have to do that with the math library and not with the input-output library or the standard input or output standard library or basically any other library that's standard is a historic reason. They thought, well, the math library needs to be special because other people might want to do their own math stuff. Or they might want their own versions of sine and cosine. So we'll go ahead and make it non-standard and force them to link it in. Some compilers and some setups, you don't have to do this. For example, on my computer, I don't have to do this, but that's because I'm using a different version of GCC. I'm using a different setup from GCC. I'm using a BSD variant or something. I don't know what I'm using. All right. So understand that you might need to bring in that -L. Right? What other functions are there? What other functions are in the math library? How do I answer that question? Ask a TA, sure. They're not going to know off the top of their head, though. Yeah, Googling is the new RTFM, math.h. Okay, I don't have internet right now. C math library. Okay, now I do. I don't know why I was having a problem with that, but a whole bunch of things that that are supported in the math library. A cosine, which is arc cosine, arc sine, arc tangent, the two-argument tangent function, et cetera, et cetera. Exp, that sounds useful. Remember that I told you that you can't just use x caret y? Well, how do you do it? How do you do it in general? Oh, sorry, this is the more general one, pow. It's x raised to the power of y. Now, that's a little bit of overkill if you're just doing squared, all right, b squared, just b times b, and you're done. In fact, the compiler is probably smart enough that if it sees you doing pow with just a simple 2 over here, it's probably going to take your code and recompile it into b times b anyway. Right? So you can use either or, it doesn't matter. Square root, ceiling, fabs is absolute value for floating point numbers, floor, fmod, and a bunch of other things that are defined. Right? So that is the modern way of doing it. Google it. Here's the old school way of doing it. Man, let's look up the definition of square root. There it is. Square root. It's in the math library. Oh, great. In fact, there are 3 different variants in this. One that takes a double, one that takes a long double, one that takes a float. A function computes a non-negative square root of x, blah, blah, blah. And a bunch of other things that you can read all about. What do you think man stood for? Manual. RTM, or RTFM if you want to be vulgar about it. The answer here is RTM, read the manual. Right? Or RTFM, and then you can understand what F is. Read the freaking manual, right? Or just Google it. Right? RTM means that you just go man, square root. What do you want to know about? You type man at the command line, you can go man, short for manual, and you can read all about it and all its return types and a whole bunch of other things. Okay? All right. Now let's get into basic I/O. What does I/O stand for? Input, output. I/O, I is equal to input, O is equal to output. Right? So let's go ahead and start with, we'll consider interactive input, which is what you did both interactive and non-interactive in your lab yesterday. Interactive input is where you prompt the user to enter a value, then you read, then read from them, right? So interactive input is achieved using the, what function was it again that you were using? Scanf, which stands for scan formatted. Right? The F is short for format. It has to be in a particular format. Let me go ahead and go over to my program here, and let's go ahead and create. Here, I'll just reuse some of this code here. I've got a value A. By the way, again, as a review, what value does A have as of line 5? Garbage. 0, who knows? I don't know. Right? Throw your hands up, say, I don't know. So let's go ahead and prompt them to enter an integer. Right? Okay. And then we'll go ahead and scan it, scanf. Now, the first part here is the format that you specify. If I'm going to be reading in an integer, I put a placeholder here, D. D stands for decimal, I think. It doesn't make that much sense. It should be I, right? For integer, but it's not. I stands for something else. And then you say, I want to put whatever value they read in from the input and put that into the variable A. But to do that, I need a special ampersand right there. For now, just understand it has to be there. If it's not there, then you saw what happens, right? It starts complaining with a very, well, not so angry green underline, right? But if I put the ampersand there, it gets happy again, right? We'll understand that later on. This is actually the memory address of A that I'm passing by reference to another function, okay? So I scanf %d, and then I'll go ahead and print out you entered %d. Same placeholder to print something out, A. Right? Now this is going to be interactive input. When I hit play here, it's going to sit there and say, please enter an integer. Scanf is just going to sit there and it's called blocking I/O. It's going to block until somebody actually sits there, types in a value, and then hits enter. Let's be a good user here and go ahead and enter in 42. Enter. You entered 42. Everything worked out fine. Let's try it again. But let's be a bad user. Let's be a pebcac user. Pebcac, problem exists between keyboard and chair. Right? So I don't have a chair up here, but if I were sitting in a chair, I would be between the computer and the chair. I would be the problem. Here I'm going to be a problem here. 10. Right? Is that a number? Nope. So predict, what's it going to read in? What's it going to say? I read in blah. What's blah? You entered 0. Why did it say 0? Well, it did read in TEN exclamation point, but then when it started to try to parse it out, it sees a T. T is not a numerical value. So it stops and says, what have I read up to this point? Nothing. And what's the numerical value of nothing? 0. So it ends up being 0 here. Right? Let's go ahead and try it again, and let's go ahead and mash the keyboard. As you saw yesterday in lab, can I represent a number that large using a 32-bit signed 2's complement integer? Nope. It was about a maximum of 2.147 billion. -1. Why? Something wacky happened there. It was probably overflow or something like that. It probably choked somewhere in the middle and then just gave me garbage values. Okay, you will get garbage values. Right? There is nothing. The standard input is unrestricted input. If you want to restrict a user to the type of input that you enter in an integer. You can't enter in a fractional number, or enter in a name, or enter in a valid email, and then they just sit there and mash the keyboard, and it's not a valid email. You need to do input validation. And input validation is a lot more complex than we've gotten to yet. And in any case, input validation is a graphical it's a user interface kind of thing. You can design graphical user interfaces there that have text boxes, and then you can restrict that text box to only numerical values, or numerical values within a certain range, or a drop-down menu that you can select from these three things, but not just any arbitrary selection, right? So input validation is much better done through graphical user interfaces and something called modal operation, where you force the user into a small subset of inputs. There's no restriction here whatsoever. You can go ahead and mash the keyboard all you want, all day long, and in fact, doing something like this is the classic attack vector for what's called a buffer overflow that we'll talk about later. There it was 0, right? Well, that's because it started with F, right? So let me go ahead and type no, let's not type too many. Let's start over again. Let's type 1, 2, 3, 4, and then hello, right? What do you think is going to happen here now that you know how I told you that it worked, that it tries to parse things until it can't anymore? Probably 1,234. It sees H, stops, says, what have I parsed so far? 1,234. Right? OK. That's interactive input that you use the scanf. So again, you provide a placeholder. The placeholders for the three variables that we've done so far, doubles would of course correspond to %LF. LF stands for long float. It's not just %F for doubles. For an integer, it would be, what did I use before? %D for decimal. Think of it that way. The only one that makes sense, though, is a char value. And this one makes sense because it's simply just %C, if you want to read in a single character. Right? In general, read one value at a time. You'll probably see a bunch of tutorials online that say, you can go ahead and read in 3 values at once, %D, %D, %D. It gets really hairy because what is the delimiter there? Is it one space? Is it all spaces? Is it any white space? And then you get into other issues that when I type and then I hit enter, enter is part of the standard input. That enter, that /n, is still in there. So you have to take that out if you want to ignore it. And there's a whole bunch of other issues. Avoid that. Avoid that simply by reading one value at a time. If you need to read in A, B, C in order to do square roots, read in A. Prompt them for B. Read it in. Prompt them for C. Read it in. Do it in that manner. Okay? You never forget your ampersand on the variable. Right? That it's got to be ampersand A if I just want A. Otherwise, you'll get weird results. What kind of weird results? Let me go ahead and go back over here, and I'm really hoping that this is giving me no, it's a warning. It's just a warning. But I can go ahead and enter this integer, 1, 2, 3, 4, 5. I'll be a good non-pebcac user here and enter an actual value that's storable. Segmentation fault. This is your first segmentation fault because you forgot the ampersand. You will be seeing a lot more segmentation faults. A segment is simply just a chunk of memory. Here's a segment of memory, here's a segment of memory, here's a segment of memory. This memory over here belongs to you because you requested it from the operating system and it was granted. This memory over here belongs to a different program that has sensitive information, passwords or something. Do you think it's a wise idea to let your program, whose memory is over here, to access this memory over here? Probably not. That's a segmentation fault. You're not allowed to access memory that doesn't belong to you. The operating system figured this out, that we were trying to access memory that didn't belong to us, and it killed our program with a segmentation fault. Right? Very good thing to happen. It's a security thing. Right? So restoring the ampersand there will result in no warnings, and of course, it's back to operational. Okay? Never forget your ampersand with scanf. You can print to the standard output, that is the screen, using, what was the other one? Printf. Right? Again, same format. You provide a format and any number of variables. In the first example that we did last week, when we were converting kilometers or miles to kilometers, we actually had two variables that we were printing at any one time. What are the placeholders here? I will do a cut and paste. Oops, there we go. Integer stays the same. It's still %d. Doubles are only %f. I think you can use %lf, but it's not necessary and it looks weird. And characters stay the same. So just a couple of gotchas, right? For scanf, the placeholder is going to be lf. For printf, it's simply going to be just %f. And f stands for float. Okay? You can print multiple values in one statement using multiple placeholders. Right? So again, let's go back over here and do an example. Instead of int a, double pi is equal to 3.14159. Right? Does anybody know? Oh, say. Oh, 1.259? 159. Is that not what I had? Okay, anyway. Let's go with my initial. C or Chris, if you don't know me yet. All right. Now let's go ahead and print all of these things out. The value of A is %d because I'm going to print out A. And pi is %f. And my initial is %c. Now I've got three placeholders here. I will need to provide three comma-delimited variables here, a, pi, and initial. And the order matters. Oh, I misspelled it here. There we go. I didn't spell it correct still. All right, we'll get it. There we go. All right, so a corresponds to the first one, pi corresponds to this one, and my initial corresponds to this one. And everything looks great. The value of a is 10. Pi is 3.14159. Where did that hell did that come from? Then we'll talk about that in a second. And my initial is c. If I screw this up, and can't spell initial today, I'll go ahead and put initial and then pi. What's going to happen? Well, first of all, it's getting angry at me. They're passive-aggressively angry at me because it's green for some reason. It should be like yellow or something, right? A warning. What's going to happen? Let's try it. The value of a is 10. That makes sense. Pi is, is it not saved? Did it fix it for me? Weird. I don't believe it. Let's go back to mine. Emacs foo.c. Get rid of this. All right, let's try it on my command line here. I don't care about warnings. Ha, okay. It's like fixing it for me or something. %f. I want the initial there. Okay, let's try. Let's really throw it for a loop here. Let's give it three placeholders, but only one value. There, finally. Pi is 0 and the initial is h. Did you see me type an h anywhere? All right. Now I'm really screwing it up and throwing it for a loop here, and it didn't fix it for me this time, right? It's because anything goes. In C, we call this undefined behavior. If you do something that is technically not against the rules, but still not a bad idea, or is still a bad idea, then anything goes. You're rolling the dice and you're getting some random values. Don't do that. Don't do undefined behavior. Undefined behavior might result in anything and everything. Right? In fact, there's an intentionally bad compiler that's maintained. I forget what it was called, but basically, if you ever try to do anything undefined, it's designed to erase the hard drive, and it's designed to do very, very bad things. And it's kind of a joke. You wouldn't want to do this, of course, but it's a joke because it's telling you don't do this stuff because yes, this is valid operation. If you do undefined behavior, it can do whatever it wants, including erasing your hard drive or something, right? So don't do something like that. You can print multiple values in one statement using multiple placeholders, but the number and types should match, right? Okay. You can also have more fine-grained control over what is printed. So let me go back to my example over here, and I'll just have pi here. I'm going to define my own pi, and I've only defined it out to 5 decimal places. Does anybody know the rest of the decimals? 2, 6. Okay, you can go out. 1,000 digits of pi in your head? No? Oh, you wish. That'd be a great, I don't know, a great conversation starter at a party, maybe? I don't know. Probably not. It'd be a great conversation ender. Right. There we go. All right, so let me go ahead and print this out. What happens? I get 3.14159, 0. That's because the default is to print out 6 decimals of accuracy. Right? Let me go ahead and grab this and put it over here, and put it so that we can see how we can change this. What I'm going to do is I'm going to print out more decimals of accuracy. Say that we want 20 decimals of accuracy. Well, did I define 20 decimals of accuracy? Nope. And in fact, can you have 20 decimals of accuracy? Remember, you're limited to about 16 or so. So what are we going to get out of this? Oops. Ignore that, and we'll talk about that in a second, why it did that. There we go. That's what I wanted. So what is it doing at the end? 3.1415, then it dies. It's doing guesswork. What should those bits be? All right? And this is an issue. One third. If I take 1/3 and add it to 1/3 and add it to another 1/3, what do I get in the real world of mathematics? I get 1. I don't necessarily get that in computers or in a programming language. 1/3 is 0.333333, 16 of those things. 0.3333, blah, 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 plus 0.3333, plus 0.3333, what is it? 0.999999. I don't get 1. Right? These are called floating point errors. And it's occurring here because it's making a guess as to what those lower end bits are. So you can't get that. Let's be a little bit more reasonable. Let's say, well, certainly we could print out 10 decimal places, right? And I didn't define what those were, so those end up being zeros. 3.14159, there's the 5 that I defined, and then I get 5 more. And then, of course, you can keep going if you really want to. 16 will probably be, there's where it breaks. 15 is okay. Yep. 16 is where it breaks. Why? Because that's about how many you can represent. I'm 16 decimal places to the right. I've already taken up 1 on the left. I don't want that. I've already taken up 1 on the left. And so that's why it breaks at 16. You can only represent 15 on the other side because you've already represented 1 over here. Well, what happens if you want to do fewer? What if I want to do, say, 2 decimals of accuracy? And note here the syntax. %, point, and then however many decimals of accuracy you want, then F. This will print out 3.14. What if I wanted to print out 3 decimals of accuracy? What is this going to print? 3.142. Why? What happened? It rounded, right? Did it change pi? Did it change the value of that variable? No, only the assignment operator can do that. I can reassign it to 3, or I can reassign it to 3.14159, 2, blah, 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 blah. Yeah. I can reset it to any one of those things. But printf doesn't do that. Printf simply says, you want 3 decimals of accuracy? Okay, I'll go out, I'll round it for you, and then print it like that. That's what appears on the screen. That's not what's stored in this variable up here. This variable still has the value 3.14159. Okay? And to prove it, I'll go ahead and print it out again to 6 decimals of accuracy, which is the default. And then again, this was 3.12. And you see that, in fact, did not change. You can print things on the other side, too. Printf. Let me go ahead and show you another formatting way to format. Let's say that we want 4 decimals of accuracy and the line pi. So how would you interpret that? Again, look at the format. %, then a number, which we were not providing before, period, then another number, then f. That second number is unchanged. We're asking for 4 decimals of accuracy. But that new number on the left-hand side, 20, that is giving me a minimum number of columns to print. So it says print at least 20 columns when you do this. Well, three point, the period counts in this. 1415, right? So how many was that so far? 6. How many are left? I want at least 20, so it's going to print out 14 something. What is that 14 something? What does it end up being? Spaces. It's going to print 20, at least 20 columns, but it's then going to justify it to the right. So how many spaces are there without me counting? Or what do we say there? We printed out 6 characters, right? 4 on the right side, the period, and then the 3. So how many are left over? 14. Right? And if you do this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Who'd have thunk? You can do, and you can also, this prints 14 leading spaces. You can also justify it to the left, right? And let me put in another character here, an exclamation point, so that you can actually see that it's doing it, right? Here are 14 spaces followed by an exclamation point, and it's justifying it to the left, right? So you can justify it right, you can justify it left. I think there might be a way to do it centered, but I'm not sure, and that's kind of weird anyway. So this prints 14 trailing spaces. And you can also do other things like printf. You can do the same thing with an integer, although it makes a little bit less sense. Int x is equal to 1, 2, 3, 4. Let me go ahead and go down here. And if I want to print, remind me, what is the placeholder for an integer? %d, and I'll print out x. That is, as you would expect, 1, 2, 3, 4. If I wanted to print out, say, a minimum of 20 columns, though, and by the way, there is no point with this, point 1, then you would want, then you're shopping at the wrong place. What do you want instead? If you want to print decimals, you want an F there. So this says print at least 20 columns with that integer, and so it ends up printing how many columns there? 16, because it's a minimum of 20. You printed 4 here, so the remainder 16 leading spaces here. But you can also do cool tricks like this. Put a 0 to 0. And what ends up happening? Oh, you know what? Let me go to the next line so that you can read it. There we go. And what ends up happening? It prints leading zeros. Why would you ever want to do something like this? Well, everybody in here has an NUID or a social security number. Think about NUIDs. How many of you have an NUID that begins with 0? It should be about 10% of you because they're randomly assigned. How many have an NUID that begins with a 00? Oh, okay. It should be about 1% of you, right? So if you ever wanted to print, say, a formatted number where you had those leading zeros, you can use a trick like this. There are use cases for this kind of stuff. Right? So it prints how many? 16 leading zeros. And of course, you can justify it left, right, whatever you want. Okay? I'll go ahead and take this and bring it over and include it as an example. All right? When I post the notes later today, or later tonight, I guess. All right? Okay. Let's see. That's all good. Questions so far? Then let's use what we've had in the last 5 minutes and write a real program here, similar to what you'll be doing tomorrow. Let's go ahead and solve that quadratic equation problem, right? We're gonna read this in from the user, enter in the coefficients a, b, and c. So printf, enter a. Right? Now, how am I going to need to read that in? Scanf. And what kind of variable should we make a? I didn't declare it, so there's no variable a yet, so I need to do that. Let's talk about this. Should I allow doubles? Like,
Well, shouldn't it be an integer because
can you have polynomials with like 1/2 x squared plus 1/3 a or b or x whatever? Yeah, okay. I'll go ahead and go with a, b, and c. If you're declaring multiple variables of the same type, you can provide a comma delimited list of these things. Right? What values do they have at line 6? Garbage, who knows? I don't know, right? So we're going to read them in. Okay. Percent, what's the placeholder for a double then? LF for scanf. Right? And is that correct? Oh, fine. Yeah, what is it passive aggressively telling me? Ampersand, please. Right? Cut, paste. I just committed a cardinal sin in programming, but for a simple example like this, it's okay. What did I do? I did copy pasta. I copied a piece of code, pasted it, and then modified it. Copy, paste, copy, paste, copy pasta. We call it copy pasta because it leads to what's called spaghetti code. So think about cooked spaghetti. Is cooked spaghetti organized? No, it's a big bowl of mash, and it's all intertwined. You can't make heads or tails of it. You don't know if that noodle is the same noodle as over here, right? Code likewise. If it's all mixed up like this and garbage spaghetti code, nobody can read it. They will have to untwine it and put all the individual noodles, go through all that work to determine, okay, this is what this noodle does. This is what this noodle does, right? Whatever a noodle does. So don't do that. Don't copy pasta code because it leads to spaghetti code. Once I've got these three things, let's go ahead and compute the root. Just one root for now. Again, it was what? Negative b plus square root of b squared. Can I do that? B times b minus 4a times a times c divided by 2 times a. Is that right? Forgot parentheses. All right, now let's see if we can get it to work this time. Printf, one of the roots is, I don't like this code completion stuff here. One of the roots is percent, what's my placeholder for a double when I'm printing? F, and the line, and I'll print out root. So if this works, I'll do something nice. 10, 110. Okay, you can pull out your calculators and verify if that's correct or not. Or you can give me one. Give me a test case that you know is correct. Say what? 1, 2, 1. What should it be? 1? Negative 1 and negative 1 maybe. Right? I'm not sure. All right. Let's try one. So when you're testing, one good strategy of testing is to use a test case of a known value. That you've taken out a piece of paper, you've written it down, you've figured it out using a method other than your program. Once you know these are the good inputs, these are the good outputs, then you can test your program and verify. If I just did the one that I did before and then went to my calculator, I'd be working in reverse. Don't do that. Let's do one more here. What else should I try? The one I was trying before was making b very small. What should it be? It's going to be imaginary. And there, now I've got nan for some reason. I don't know why it was screwing up before. It was really screwing up before. In fact, it's negative nan, right? Negative, not a number. Well, if it's not a number, how can it be negative? It doesn't make any sense. Give me one last one, and then we can go. What's another weird one that I should probably test? Can you have a coefficient of 0 on a quadratic? Yeah, it just makes it linear though, right? And it makes it a different problem. Is that going to lead to a problem with this program? It's also nan. Why? Because of the denominator, right? That's why the quadratic formula doesn't work for linear functions, right? So you're using the wrong tool for the wrong thing, right? Have fun and hack.